We have one application problem left. Let's check it out. A rock is thrown upwards on Mars. Its height follows h of t equals negative 1.86 t squared plus 9.3 t, where h is in meters and t is in seconds. So someone's standing on Mars and they find a rock and they just throw it upwards. I don't know if it's as hard as they can or what, but they throw a rock, and obviously the gravity is less on Mars, and so they really get a good throw. We're going to look at how long it will take until it comes back and hits the ground. And then obviously where we want to go with that is what's the instantaneous velocity as it strikes the ground. Okay, let me switch over here. There you go. There's our height function. And how many seconds, we need to know this first, how many seconds after it's thrown will the rock finally make it back down to the surface? For this, there's no calculus. We just recognize, well, if I know the height function, then how can I figure out the time when it gets back to the ground? Well, when it strikes the surface or strikes the ground, that's when the height is 0. So I can set this equal to 0 and solve for t. It turns out, even though we have these decimal numbers, if we factor out negative 1.86 t, this is going to work out okay for us. So factoring this would leave t minus, let me just grab my calculator here, 9.3 divided by 1.86 turns out to be 5. And that gave us some good numbers here. So with these two factors, right, we can set them both equal to 0 and solve. Well, one moment will be, when it's, I guess, when the rock is thrown, like, I don't know if it was thrown from the surface level, but that's kind of when we're thinking of time 0. How many seconds later will it take to strike the surface? And it comes down right at 5 seconds. So this parabola is kind of like, at time 0, it's on the surface and it gets thrown, and then it hits again there at 5 seconds, right? Okay, so 5 seconds later is our answer. We want to know the instantaneous velocity as it strikes the surface. How fast is it going when it hits? That's important, right? It depends on how high up it got. To find the instantaneous velocity, we'll recognize, okay, right? They're talking about the derivative. At the moment it strikes at 5 seconds, we need to find h prime of 5, the derivative at 5 seconds. All right. Now, at this point, we could use either derivative formula from this section. I'm going to go with the original formula. It's going to go a little bit faster. It tends to be a little bit faster. So let's just go with that. We're going to take the limit as t is our variable now. As t approaches 5, h of t minus h of 5 all over t minus 5. Okay. Sharpen my pencil. So h of t, well, that's our function, negative 1.86 t squared plus 9.3 t minus h of 5. Okay. Well, we actually already know this, but let's just go back and plug 5 in. What is h of 5? Negative 1.86 times 5 squared plus 9.3 times 5. Oh my goodness, what is it? Well, it's 0, of course. Because that was the answer for the height. We knew that. We knew the height was 0 at 5 seconds. Okay, so we can basically ignore that, right, since it's 0. Well, negative 1.86 t squared plus 9.3 t over t minus 5. We'd really like to plug 5 in, but that'd be 0 over 0. So that's not going to work. We're going to factor, and it's going to be the same factoring that we did a moment ago. And that will cancel out the t minus 5. Kind of cool. T minus 5s cancel. The limit as t approaches 5 of negative 1.86 t. And we'll have it. Is that going to give us negative 1.86 times 5? Negative 0.93. Oh, okay. Interesting. Yeah, there it is. What units would we have here? I mean, we've got an application, we've got a word problem, so it'd be nice to answer with units. I don't think I copied those over here on my page, but it had told us that h was in meters and t was in seconds. So if we're talking about h being in meters and t being in seconds, then our derivative, it's a rate, right? The instantaneous velocity. This is meters per second. There you have it. Okay, hey, that's our section. Check out the homework.